Picture this. You are seated in a spacecraft of extraordinary design, alone in the silent darkness of space. Without warning, its engines ignite, not gently but with a ferocity beyond all human experience. Within a single second, this machine propels you towards the speed of light, a feat as breathtaking as it is impossible by any conventional measure. In that brief heartbeat of time, the inertial forces around you surge to a staggering 30.6 million times Earth's gravity. You began this journey with a mass of 80 kilograms, but now the resistance you feel could be likened to carrying billions of kilograms. You are pinned, not by a planet's pull, nor by any star's immense grip, but by pure acceleration itself. Now pause. In your immediate experience, it makes no difference why you feel these colossal effects. If you knew nothing of engines or rockets, you might swear you were ensnared within the deepest well of a monstrous gravitational field. Here, Einstein's equivalence principle takes center stage. It whispers, locally there is no test, no instrument, no clever trick that can distinguish acceleration from gravity. You find yourself at a frontier where these concepts converge so closely that the difference between them ceases to matter. This is not gravity reaching out across space to yank you down. This is geometry made manifest. In general relativity, gravity is not a mysterious force. It is the shape of spacetime itself. Your craft's furious acceleration and the presence of a massive object curving spacetime share a secret symmetry. In both cases, you feel the same inexorable load, and in recognizing this, you begin to glimpse the extended limits of our conceptual tools. Traditionally, physicists have leaned on frames of reference to tell their stories, imaginary scaffolds on which to hang measurements of time, distance, and energy. They've been indispensable guides from Newton's era into Einstein's revolution. Yet here, at this extreme edge, the notion of an external observer begins to unravel into abstraction. From far away, another watcher might say you've slowed down, that your length has contracted, that strange horizons have formed around you. They would claim their chosen frame of reference explains what is happening. But to you, that commentary is unnecessary. The profound reality you are living through does not bow to their viewpoint. The intensity of your local conditions is absolute and immediate. No distant frame can dilute it. Each of these frames that once felt so essential now appears as a stepping stone, valuable but not ultimate, as we journey deeper into the heart of spacetime's geometric truth. Step back, far back to cosmic scales, and similar lessons arise. Timescape cosmology suggests that what we perceive on the grandest stage of all, the evolving universe itself, may also hinge on local gravitational differences. Subtle pockets of varied curvature and matter distribution influence how clocks tick and how rulers measure space, shaping our interpretation of cosmic expansion. Just as no global frame is needed to comprehend your moment of extreme acceleration, perhaps no single universal vantage point can capture the complexity of the universe. Instead, the cosmos may be a mosaic of local stories, each region telling its own tale through tidal forces and the interplay of matter and voids. All of these local truths knit together into a grand narrative that no single frame can fully describe. We should not deny that frames of reference led us here. They were once our best maps, guiding us from static absolutes into a dynamic, curved reality. They remain indispensable for practical predictions and everyday observations. Yet this thought experiment, by invoking unimaginable accelerations and hinting at cosmic inhomogeneities, reveals a threshold beyond which frames yield diminishing returns. Beyond it, we confront a more direct understanding of reality, one that emerges from local conditions and intrinsic geometry, not distant observers. The equivalence principle's hushed counsel applies here as well. It whispers, again and always, that locally there is no test, no instrument, no clever trick that can distinguish acceleration from gravity. And just as no external frame can fully encapsulate the intensity of your experience, no single overarching perspective can fully capture the universe's intricate structure. No, we need not romanticize this state of affairs. The sheer numbers, 30.6 million g, billions of kilograms in effective weight, are only there to illuminate principles holding true at any scale. When confronted with such extremes, our familiar scaffolds fall away, revealing only the underlying geometry. What happens to you, right where you are, transcends any distant commentary. From the event horizon of a black hole to an accelerating rocket, from local gravitational pockets to cosmic inhomogeneities, the message is the same. Local conditions rule supreme. Frames of reference, once central to our understanding, are stepping stones rather than final foundations. In the end, this is the true legacy of such a thought experiment. It encourages us to recognize the limits of our conceptual tools. Beyond those limits, we uncover a deeper understanding. Reality is stitched together from countless local patches of space-time, each with its own inherent logic, each telling its own part of the universal story, without ever needing permission from a distant frame to be what it is.